Okay, let's go on to section 4.2. So section 4.2 is antiderivatives, based on integrals kind of things. Okay. Now, so if we have f, so this big F is holomorphic in G. So remember that just it's any little neighborhood in G, F is differentiable. Okay, so it's pretty much differentiable everywhere if G is a region. Yeah, well, in G, a region, we make it that way. Okay, and if I take the derivative, since it is differentiable, and I get f of z, then f of z is an antiderivative, not the antiderivative, but an antiderivative of f of z. Same idea as real numbers, so is f of z plus a constant, arbitrary constant. Okay, so here's our basic theorem, 4.11. Here is our fundamental theorem of calculus idea. Okay, so we've got G, subset of the complex numbers is a region. And gamma in G for gamma of T, and I'm going to use T1 less than or equal to T less than or equal to T2, like that. Okay, so we've got a region, we've got a path in that region, a smooth path, piecewise smooth anyway. Okay, so if we have that, if f is continuous, and f an derivative of f, left, then the integral, this integral of gamma over gamma of f, which we would write usually as the well, I'm not going to write that. I'm just going to write the fundamental theorem of calculus idea. So this is gamma of T2, f of gamma of T2 minus f of gamma of T1. Okay, so it's path independent. Any path from A equal gamma of T1 to B equal gamma of T2, any such path, it's a nice, a piecewise smooth path, this says give you the same answer. So that's just like what we think of with real numbers. Right? And And so this is a biggie. That's a technical word. We're saying that I've got some region, and I'm going from this A, over here to B. It really just doesn't matter how we do it. Path independent. Integral. Okay, so the key is you need something that has an antiderivative, and so we can kind of check that out. If we go back to example 4.1 again. Okay, and we had a couple of these paths. We had a path here. This was A. And we had a path that went like that. That's B. As in 4.1a, 4.1b. One was the straight line. The other was y equal x squared. And this is 1 plus I. Then now if I let f of z equal 2z, then notice that antiderivative f of z, one antiderivative would be z squared. And so according to this, if I want to do path gamma of 2z dz, and I want to go from 0 to 1 plus I, then the answer to that is I should get f of 1 plus I minus f at 0, and well, that's 1 plus I squared minus 0, and that is 1 plus 2I minus 1, so we get 2I. Okay, according to this, the fundamental theorem for these holomorphic functions, I should get 2I. So if we look at part A, again, that was the gamma was equal to t plus it, 0 less than or equal to t less than or equal to 1, and of course gamma prime then was 1 plus I. Okay, so we just do that integral this way. So I want the integral from 0 to 1 of 2 times gamma, so t plus it, because it was 2z, and then times gamma prime 1 plus I dt. So this is equal to 2 times 1 plus I times that integral from 0 to 1 of t plus it dt. And so this is 2 times 1 plus I times, and we'll get a t squared over 2, so that's a half, plus I t squared over 2, so that's a half. Like that. Well, use the 2 there, and you see what I get is 1 plus I squared, which we now know is 2I. So we ended up at that same, here we had the 1 plus I squared and simplified it to 2I. 1 plus I squared, simplified it to 2I. So that was A. Here's B, was the gamma was what, t plus I t squared. So gamma prime is 1 plus 2it. Well, this also went from 0 to 1. And so, we do that integral, 0 to 1. And we had 2z, so this is 2 times t plus I t squared times 1 plus 2it dt. So I'll factor that 2 out. It's 2 integral 0 to 1. Multiply this stuff through, so the 1 times that stuff, I get t plus I t squared. And then the 2it times that stuff, I get plus 2i t squared and a minus, minus 2i, or not 2i, but minus 2, t cubed dt. Okay, so these I can put together as 3it. So we'll just do that antiderivative then. We get t squared over 2. There were 3 of these it squared, so we'll get plus 3it cubed over 3. And then minus 2t to the 4th over 4 from 0 to 1. So this is 2 times 1/2 plus I minus 1/2. Don't need to do 0, we get 0. So this is equal to 2i. So that same darn answer again. So it looks like, yeah, this really does work. So let's see. Did I already mention the? Gotta go back here. Okay, path independent. No, okay. I did not. I didn't think I had, but now, so consider a closed path. Now that is gamma of T1 is equal to gamma of T2. Right, so we were out here somewhere and we go like that and we end up back where we started. Then in that case, if f satisfies all the conditions in gamma, in a region G and so forth, then f of z dz, well, that would be equal to our antiderivative at gamma of T2 minus f at gamma of T1. But since those 2 points are the same point, we get 0. And this was this is corollary 4.13. Okay, so if we have these nice functions with antiderivatives, then if you do a closed path, you get 0. And so they give a quick application of this, actually. Example 4.14. They're looking for existence of a derivative. Okay, of a derivative in a region. Okay, could be like a closed disk or something like that. Okay, so they say, well, let's let little f of z equal 1 over z, and the question is is this differentiable running out of room there. Is this differentiable in, and they used, I think, the unit disk, yeah, in the unit disk. So what we do is we then let gamma of t be e to the it, so 0 less than or equal to t less than or equal to 2 pi, and that means that gamma prime of t is equal to I e to the it. And let's set up that integral. So we do the integral over gamma of 1 over z. Well, that is the integral from 0 to 2 pi of 1 over e to the it times I e to the it dt. And so the exponentials cancel, and we get the integral from 0 to 2 pi of I dt. And that is 2 pi I, not 0. So f is not differentiable. Everywhere in the unit disk. Okay, because otherwise we should have gotten 0, but we got 2 pi I. And we're just about there then. So theorem 4.15. Okay, once again we've got G is a region, and we'll talk about some Z0 in G. And this is like the second fundamental theorem of calculus, where you're doing, okay, so I'll put in parentheses here, like defining f of x as the integral from some x0 to x of little f of t dt. Okay, this is the idea that we're getting here. And so what do we need? We need we'll call it gamma z is any piecewise smooth curve, or path, I guess we say, path in G from z0 to z. So, you know, we're looking in this region, there's z0, and we're just saying we're heading out here to z. There's some path. Okay, so we need f to be continuous, so f of z is continuous. And such that the integral over any closed path of f is equal to 0 for gamma, a closed path in G. So, you know, if I've got this nice function that came from a holomorphic function, it's the derivative of some function, then and that's what this is saying. You know, we need to have nice functions. But if we do that, then we could define our antiderivative f of z as being equal to this path integral from z or z. I would write, I don't know what they put in the text, but I would put z naught myself, but they may not do that. F is an antiderivative antiderivative of f on g. Okay, so you know, in essence, we're talking about doing something like this, defining an antiderivative by the integral of its derivative. Okay, and I think that does it for 4.2. So we'll escape out of this and turn this off.